and the citric acid cycle, okay, because of that. And then I'll use, what I got, blue, just so we can keep track. I'll use blue for electron transport. Okay. Just to keep track. Now, these are all our scenarios, right? We know that there's a difference between theoretical and realistic yields, right? Theoretic yields are yields under optimal conditions in a lab. If I could make everything go to its maximum, that's what I would get. And we know that that's 3 ATP per NADH that goes into the electron transport chain and 2 ATP per FADH2. Now the way to say it is that there is enough energy released from NADH as it passes electrons through the electron transport chain to phosphorylate 3 ADPs to make 3 ATPs. So that's what we're saying. Under most realistic conditions inside a cell, rarely do we have those theoretic optima reached. And it's more realistic that if I fed an NADH into the electron transport chain, the electrons from NADH in the electron transport chain, I'd release enough energy to drive the synthesis of 2.5. If the electron source was FADH, it's a lower energy electron, it would be enough to drive the synthesis of 1.5. So those are our conditions. Now, okay with that? The other thing we have to keep in mind is that there are also differences between two different kinds of cells in the body. Most cells in the body cannot receive this cytosolic NADH. Now, where did this come from? What process produced this NADH in the cytosol? Glycolysis, and there should be 2 of them, right? In glycolysis. In most cells in the body, because of the energetics and whatever, and the enzymes that are expressed, those electrons cannot be fed directly into the electron transport chain of the mitochondria. They first have to be given to FADH2, and then that can transport them into the electron transport chain. So all this does is change bookkeeping. Right? It's not magic. I'm just telling you that most cells in your body cannot receive cytosolic NADH, but they can receive cytosolic FADH. So what do? They take the electrons from NADH and they give them to FADH, and FADH brings them in. But why does that matter? That matters because of this, right? So that means here you're being punished by 2 ATP always, right? Because you can't get it under either condition. You can't get the full amount of NADH. You're always going to be reduced by that 1. Is that okay? So that's what that means. However, there are 2 cells in the body, hepatocytes and cardiac myocytes. So cardiac muscle fibers in the heart and cells in the liver. And that should make sense, right? Because those cells are have an incredibly high demand for ATP. Right? They do a lot of work. In fact, I would argue that neurons are maybe the only other exception, but cardiac muscle cells and hepatocytes do the most work in the body. Here, they can receive the electrons from NADH in the cytoplasm. So it's only under this condition here in these cells where you're ever going to get the full amount, right? And our numbers that we want to come up with, right, are if you get theoretical yields, you're going to get either 36 in a typical cell or 38 under a liver or cardiac. If you're under realistic conditions, you're going to get about 30 ATP in a typical cell, and you're going to get about 32 in a cardiac cell. Here's why. So what do we got? How many ATP come from glycolysis? What do we get as far as ATP from glycolysis?
2.
So glycolysis is going to give us 2 ATP. The other energy that I care about here is energy in NADH, right? And I have how many NADH? 2 NADH. Okay. Can I use those electrons in NADH here directly into the citric acid cycle? No, because it says what? They have to enter as FADH. So let's say here, I'll use black just because we're here. We're going to take those 2, we're going to transfer the electrons right away because I can't use them in that form. And I'm going to go make 2. Now what did I just tell you? I'm going to oxidize NADH and reduce FAD. Meaning I'm going to take the electron from NADH and give it to what? FAD. That's all I did. Okay with that? Is that good?